Previously, we went over the very basis of permutations. In this video, we will elaborate on permutations and introduce indistinguishables. We will start with a setup where we have the same amount of objects as we do positions. This is just a refresher from the last lesson. Currently, we have 7 mugs and 7 positions. There are 7 different permutations for this setup. Instead of manipulation of the mugs, we'll consider manipulation of the positions. This approach isn't common. It involves changing our perspective of the roles of positions, but positions are distinguishable objects just like the mugs. So instead of moving the mugs, we can move the positions. It doesn't seem like a big deal at first. I mean, what difference does it make if I change the positions around instead of the mugs? That's like switching the positions of the boxes the mugs are in instead of switching the mugs in the boxes. The difference is, our last equation only works if you have limited positions and plenty of mugs. But what if I have plenty of positions or containers, but not enough mugs? The equation breaks because you get a negative in the factorial. It doesn't work, so we have to change our whole perspective of the problem. Let's remove 3 of the mugs and set the remaining positions to the side. We can rotate through the positions just like we did the mugs. So, in a way, we invert the entire equation. The mugs take the role of positions, and the positions behave like the objects themselves. So now we can conclude that the equation for the circumstance where there are more positions than there are mugs becomes positions factorial over positions minus objects factorial. Seems simple enough, right? This is an important point. Although it's a simple concept, it's what's necessary for visualizing indistinguishables. So let's get into it. Let's pick any mug and make it similar to another mug. Then, to make it easier on our eyes, let's place that mug beside the other mug that is similar. We can rotate these mugs any way we like, and it won't make any difference at all on how the mugs are arranged. So, in the grand scheme of things, the order of positions 1 and 2 doesn't really matter. In fact, it wouldn't matter what 2 positions those mugs are in. The 2 positions will have identical objects. So let's start building our equation. Let S sub 0 be the permutation of distinguished mugs. Let S sub 1 be the permutation of the indistinguished mugs, and capital S will be the total number of permutations. First, we count the number of distinguished mugs. In our case, there are 5: red, white, pink, green, and yellow. But keep in mind, there are 7 positions to consider, so the number of ways to arrange the distinguished mugs is 7 factorial divided by 2 factorial. Now we put our attention on the indistinguished mugs. There are 2 of them, but they will only be in 2 positions. The other 5 positions were taken by the 5 distinguished mugs. Therefore, there are only 2 factorial arrangements. Now, we combine the 2 arrangements. If we wanted to consider the order of the indistinguishables, we multiply them together. This would give us S. When we do this, we see that the 2 factorial gets canceled out of the denominator of the distinguishables. We already knew this was going to be 7 factorial, but the important part is we use 2 pieces to find that number. Now comes the trick. We want to ignore the indistinguishables since order doesn't matter. We can do that by simply ignoring the 2 factorial. Essentially, we're not multiplying it back into the distinguishables. You can say that we're dividing them out. This brings us to the result. If I have 7 mugs and 2 of them are indistinguishable, then I divide out the permutations of the indistinguishable. 7 factorial divided by 2 factorial. So let's generalize this. If I have an n amount of mugs and k of them are indistinguishable, then I will have a total of n factorial divided by k factorial permutations. Let's build on this. Let's make the problem a bit more complicated. So, I just divided out the permutations of the indistinguishables, right? Well then, what if I had 2 sets of indistinguishables? What do I do then? Well, not much changes really. The same idea applies. We just divide it out like we did the last one. So we would be dividing out 2 factorial twice, since there are 2 sets of indistinguishables that each have 2 mugs. This is all we have to do. Take the total number of objects and count how many mugs are in each indistinguishable. We take the factorial of the total number of objects, 7, and then divide it by each number of indistinguishables, 2 and 2. Generally, we take the factorial of the total number of objects and divide it by the number of each set of indistinguishables. It really is that simple, although it may not be very intuitive at first. So maybe this isn't totally convincing, so let's look at it a different way. Let's create a set of unknown mugs and set them to black. So the point is, we don't know if each black mug is distinguishable or not, but we do know that the number of ways we can move the blue mugs is 2 factorial, and we're going to use that to our advantage. Since we don't know how we can arrange the black mugs, we'll just label it with an unknown variable, t sub 0. I know it might be a bit frustrating to consider, because we are going to count how many ways we can arrange these mugs without knowing how many ways we can arrange a certain group of them. We will keep the t sub 0 unknown and consider the blue mugs. We know that, whatever the t sub 0 is, we can multiply it by 2 factorial if we want to include the arrangement of blue mugs. And this is where the magic begins. Now, let's consider moving the blue mugs to a different position. The new setup doesn't change anything except positions. The math is the same, but the setup is different. So we will say the setup is t sub 1 times 2 factorial. If we want to combine each setup, it is the entire quantity of the t sub 0 and the t sub 1 multiplied by the 2 factorial. We can be confident that this will be the case for all the setups. We don't really know how many setups there are, but it isn't important. We just make that sum equal to t. And since each setup was multiplied by 2 factorial, t times 2 factorial equals s. Remember, we use the s to symbolize the total number of arrangements if we cared about the positions of the blue mugs. This is an important part because s should be known. T represents the arrangements if we don't care about the indistinguishables. This is the number we want, so we solve for t, which is s divided by 2 factorial. Yet again, we are simply dividing out the permutations of the indistinguishables. So if we transform the mugs back into the original problem and reveal what the unknown mugs were, we should know the number for s, 7 positions, where we only consider the 2 black mugs as indistinguishable. S is 7 factorial divided by 2 factorial. Now we can roll right into neglecting the order of the 2 blue mugs. We simply divide by 2 factorial, which is the same result we got before. So now it can be restated. If I have n amount of mugs and I have several sets of k of them indistinguishable, then I will have a total of n factorial divided by each k factorial permutation. Now let's go into an example. I have a total of 7 mugs, 2 black, 3 blue, and 2 red. How many ways can I arrange them? The answer? 7 factorial divided by 2 factorial times 3 factorial times 2 factorial, because I have that many colors of each mug. I really hope this is helpful for you understanding indistinguishables, and happy mathing!